Jai Hind dear students, in this video we will start with the MOSFET current equation derivation. We will see the MOSFET current equation, and then we will discuss the small signal model of the MOSFET. So, these two topics we will try to cover in this video. Okay. So, we will start with the MOSFET current equation. So, we know the structure of MOSFET. It is something like, here we have N positive material, here also we have N positive material, and this is nothing but P type substrate, and then here we have oxide layer. This is oxide layer, SiO2 layer. Then we have a metal layer, and this is your gate terminal. This is nothing but your metal layer, and this is your gate terminal. This terminal is source terminal, and this terminal is drain terminal, and this terminal is the bulk terminal, right. So, this is a structure of the MOSFET. Now, what we are trying to find, we will find the expression, or we are trying to find the expression of the current ID, drain current, right. So, as we know that current can be written as charge flowing per unit time, or charge per unit time. So, ID we can write, ID should be is equal to delta Q upon delta T. Now, our aim is to find this value of this delta Q and the value of the delta T, right. So, delta Q, or this charge, is separated by, when we actually when we are applying the voltage at the gate terminal, then the positive charge will accumulate or positive charge will appear at the metal, and the negative charge will accumulate near the this SiO2 or as oxide and semiconductor interface, right. Positive charge will go to will accumulate on the metal, and the negative charge will accumulate in the near the interface of oxide and the semiconductor, right. And this charge is separated by the this we can say oxide, okay, oxide and the metal. So, this region is behaving like a capacitor, because we can see here we can consider this is a one plate, and there is a positive charge on this plate, and below we can see here we can consider this is one plate which have negative charge, and these two plates are separated by the oxide, okay. So, if we want to find out this delta Q, so this delta Q can be written as C into delta V, right. So, which is the what is the value of this capacitance C? So, it should be the gate capacitance Cg, right. So, Cg into delta V. Now, what will be the value of Cg? Cg, it should be is equal to epsilon into A upon D, right. As we have seen that charge is separated by the oxide, so this capacitance should be the gate capacitance. So, in this sequence, this permittivity should be of the oxide, it should be epsilon OX, and simply area we can say, suppose if this is the oxide, if this is the, we can say the length of the oxide is L, and the width is W, and its depth is, we can say D, or we can say TOX, right. So, the area can be written as epsilon OX, we can replace this A by W into L divided by the thickness of the oxide, which is TOX. So, Cg can be written as epsilon OX into W into L divided by TOX, right. Then what will be the value of delta V? This delta V will be is equal to, right, this delta V, it should be is equal to the voltage at the gate terminal, that is VGS minus VTH, right, minus voltage that is on the, we can say voltage just below the interface of oxide and semiconductor. So just below the interface. So what should be the voltage here? Here we can see if we apply the voltage at the drain and source terminal, then we will apply the positive voltage here, right? So voltage VDS will be available here, and this source terminal will be connected to the ground. So the voltage at the source will be 0, right? So when we are moving from this end to this end, the voltage is decreasing from VDS to 0. So in this case, we can take the average of this voltage. So here the voltage delta V will be VGS minus VTH minus half of VDS. So this will be the value of delta V. Now we can put these values in this equation, right? So we can find the value of delta Q. So delta Q will be is equal to, the value of CG is epsilon OX into W into L, epsilon OX into W into L divided by TOX into value of delta V, which is VGS minus VTH minus half of VDS, right? So this is the value of delta Q. Now this value we have calculated. Now we want to calculate delta T, right? So delta T, we can say time is equal to distance upon velocity. So suppose distance is x and velocity is v, right? So what distance carrier have to travel? What distance carrier have to travel? Basically the length of the oxide, here we have considered L, and here this same distance, we can say this is the channel length. So this length and the length of this oxide will be same, right? So charge carriers have to move or have to travel this distance L, right, with velocity v. So this x can be replaced by L, and what will be the velocity? As we know, the formula of mobility is nothing but the drift velocity per unit electric field, right? So here this v can be replaced by mu into E. Okay, so here we can write mu into E. Now again we know this electric field can be written as voltage divided by the distance, right? So the voltage here, it should be VDS and the distance should be L. So we can replace E by VDS upon L. So here in this equation we can write L upon mu into VDS upon L. So it will be L square divided by mu into VDS, right? So this will be the value of delta T. Okay, now we can find ID. What was ID? It is delta Q upon delta T. We have the value of delta Q, so put it here. So epsilon OX into W into L divided by TOX into VGS minus VTH, VTH is the threshold voltage, minus half of VDS, right? This divided by delta T. Divided by delta T is L square divided by mu into VDS. After solving this, we will get ID is equal to epsilon OX or mu epsilon OX divided by TOX into W divided by L into VGS minus VTH into VDS, right, minus half of VDS square. Okay. Now, as we know, COX can be written as epsilon OX into A divided by TOX, right? So if I try to accommodate this area, so I can write it as COX prime is equal to epsilon OX divided by TOX. So this is the capacitance and this is the capacitance per unit area. So in this equation, I have the term epsilon OX divided by TOX. So I can replace this term by COX prime. So I can write final equation ID will be is equal to mu into COX prime into W by L into VGS minus VTH into VDS minus half of VDS square, right. So this will be the final equation of the drain current, okay, and this equation is valid for the ohmic region, okay. This equation is valid for ohmic region or triode region, ohmic region, or we can say triode region, right. For saturation region, second case we can consider, this is the first case, we can say first case is for ohmic region or triode region, we have calculated the value of ID, right. Then for saturation region, we have to apply some conditions. For saturation region, we know this VGS should be greater than VTH, right. This is the first condition, and your VDS will be is equal to VGS minus VTH. It should be equal or greater. Okay, so if we put the value of VDS in this equation, then ID will get changed. So ID will be mu into COX prime into W by L into VGS minus VTH whole square minus VGS minus VTH whole square divided by 2, right. So after solving this, we will get ID is equal to mu into COX prime into W by L into VGS minus VTH square divided by 2. So this will be the current equation for the saturation region, and previous equation was for the ohmic or triode region. So as in MOSFET characteristics, we can see there are two regions only. So this is suppose ID and this is VD, and here we can see this graph generally we obtain. So here we can see here this is the triode region or ohmic region, ohmic or triode region, and after this when current is constant, this is the saturation region, and in both case we have find out the current equation. This voltage should be it should be VGS minus VTH, right. So this is the current equation we have derived, right. The next topic we will see in this video is the small signal model of the MOSFET, okay. So here we have seen next topic is a small signal model, of the MOSFET. So in previous section we have seen the ID current is depending on, or it is the function of, ID is the function of VGS and VDS mainly, right. Now if we make small changes in VGS and VDS, then there should be small change in ID. So if we consider we are changing this VGS by delta VGS, small change in VGS, and similarly we are doing a small change in VDS. So for example, this is VDS plus delta VDS. So there should be small change in ID, and it should be ID plus delta ID. Delta ID is the small change. Okay, then now we can do the Taylor series expansion, and we can write it as ID plus delta ID. It will be is equal to F VGS comma VDS plus del ID over del VGS into delta VGS plus del ID over del VDS into delta VDS, right. now we can see this ID and this function, they are same as we have written here. Okay. So ID is corresponding to this ID and this function is again is it is written here, right. So this delta ID is, we can say, it is mapping with this term and this term ID is mapping with this term, right. So we can separate them out. So we can write here this delta ID should be is equal to delta ID upon delta VGS into delta VGS plus delta ID upon delta VDS into delta VDS, right. Now if I change these notations as I change delta ID to ID, I change delta VGS to VGS and delta VDS, I can write it as VDS, right. So this equation will be ID is equal to delta ID upon delta VGS, delta ID upon delta VGS into VGS plus delta ID upon delta VDS with VDS. Okay. Obviously this value we have calculated by keeping VDS constant and this value we are calculating by keeping VGS constant. Okay. Now what is this del ID over del VGS? This is nothing but the transconductance. Okay. So ID, this can be written as GM into VGS, right, plus, and what is this del ID upon del VDS? This is, we can say, GD into VDS. What is this GM? GM is the transconductance. It is a transconductance. And what is this GD? It is the drain conductance. It is a drain conductance, right. This GD we can write it as 1 upon RD. Okay. So GD will be 1 upon RD, or this equation we can again modify. ID will be GM into VGS plus 1 upon RD into VDS. So this is the final equation of a small change in ID current, right. Now using this equation we can draw the equivalent circuit. Okay. So here if I again write this equation, what we have obtained, ID is equal to GM into VGS plus 1 upon RD into VDS. So using this equation, if I try to draw the equivalent circuit, then it should be something like this. So here if I have drain terminal here, right, this is our drain terminal, then here I have a current dependent, voltage dependent current source, and the value of this is GM into VGS, and then I have a resistance RD, right, and here I have voltage VDS, and as this current source is depending on the VGS value, so we can take here gate terminal and this is our source terminal here. So the value or the voltage between this terminal and this terminal is VGS. So this will be the equivalent circuit, or we can say a small signal model of the MOSFET, right. Now you can find the value of GM and RD or GD for linear, or we can say for ohmic region and for the saturation region. So for that you have to use the current equation that we have derived. For linear region we have derived ID is equal to mu into COX prime into W by L into VGS minus VTH into VDS minus half of VDS. This was the equation for linear region, and similarly we have obtained for saturation region, this one was for linear region, and now for saturation region for saturation region ID was mu into COX prime into W by L into VGS minus VTH whole square divided by 2. This was the equation for the saturation region. We can find the value of GM and RD for these equations, right? If we want to calculate GM, what we have to calculate? So GM should be is equal to del ID over del VGS. Okay, so we have to differentiate this equation with respect to VGS. Again, we have to differentiate this equation with respect to VGS. Similarly, if we want to find out GD, then GD will be del ID over del VDS. So we can differentiate these equations with respect to VDS, and we will be able to find out the value of GD. Okay, and GD is nothing but 1 upon RD, and then we can find the value of RD by inversing the obtained value. Okay, so this is the way we can do the small signal analysis of the MOSFET, right? Now we can use the any DC biasing that we have studied in MOSFET. We can use fixed bias, we can use other biasing methods, self bias or voltage divider bias. So we can apply these methods and we can perform the small signal analysis of the MOSFET. Okay, so by this way we can perform the small signal analysis of the MOSFET. Now we have studied different DC biasing methods, like we have studied fixed bias method, we have studied self bias method and voltage divider method, right? So we can use any one, we will see by using any one. So if we have the circuit like this is drain resistance RD, right, and we have a MOSFET here. This is RG resistance, here we have source resistance RS, this is source resistance RS, this is your gate terminal, drain terminal and source terminal, and here we have VDD supply. Here the current ID is flowing from this current source current is flowing, and from here this gate current is flowing, and here if we use the capacitor C1, and from here we are taking the output, this is capacitor C2, right. So for this circuit, what we can do, we can replace this part by the model that we have discussed, and then we can put these resistance RD and RS. Okay. Similarly, if I use a capacitor here, that is bypass capacitor, okay, we can say this is CS. Now for this, if I want to perform the AC analysis, then what I have to do, first I have to remove these capacitors, because when we do AC analysis, what we do, we short circuit we short circuited all the capacitors, and we also remove the DC supply. Okay, so we will remove this VDD and also these capacitors. Okay, so the circuit will be equivalent circuit, we can say will be, here we have RD which is connected to ground, here we have gate terminal and resistance RG is connected here, this is resistance RG. Because we have shortened this capacitor CS, so the existence of this RS is no more, right. So we can say this is directly connected to the ground terminal, and this is your source terminal, this is gate terminal, and this one is the drain terminal, right. Now if I replace this part by the model that we have discussed, so the equivalent circuit will be, here I have gate terminal, this is your source terminal, between gate and source we can see, between gate and ground, because source is directly connected to the ground, now between gate and ground there is a resistance RG. So if we look from input side, this is your input side, so we can see here a resistance is connected which is RG, in case if source is connected to the ground, right, source is connected to the ground, and here the voltage will be VGS. Okay. Similarly, here we can have a current source, value of which will be Gm into VGS, and then we have resistance RD. Okay. Then between drain and ground we have a resistance RD. Okay. So we can put this resistance also. This is capital RD resistance. This is RD resistance, and this one is your drain terminal. Again, this is your source terminal, and here the voltage will be VDS voltage. Okay, and here the current will be ID current. So by this way we can draw the equivalent model, or we can perform the AC analysis of the MOSFET, right? So now we can find the value of input impedance, we can find the voltage gain, we can find the current gain, we can find the output impedance by analyzing this circuit. So this is the way. Similarly we can do for the self bias, similarly we can do for the voltage divider bias. Okay. So in this lecture we will stop here.